Our last talk is Gary Feyereisen, and he is with the USDA Agricultural Research Service and also an adjunct assistant professor at the University of Minnesota. His research focuses on the management of nutrients in the plant, soil, and atmospheric environment to increase nutrient efficiency and reduce environmental losses to water resources. So, Gary, thank you so much for being here today.
It's okay. Thank you, Bruce. Thank you to the organizers for inviting me here. I'm a research agricultural engineer. I also thank you for being here. I anticipated being the last one up, and I think it's very appropriate because we've talked about what to do with nitrogen at the field scale, how to manage it as well as possible, how to put perennial crops in place to reduce the losses and so forth. And yet the system is leaky. The biophysics are some of the nitrogen will get into the water when we have the excess rain that we've talked about in the trends. And so my talk is going to focus on what do we do with the treatment of the water then that leaves the edge of the field and the edge of the watershed. So thank you very much. So I've framed my talk around three questions, basically. Why treat the drainage water? The second question is, what is a bioreactor and how does it work? And then the third question is related to a research project that we've been doing for the last few years. It's 40 miles south of here. And that is the question that you see before you, can water or woodchip bioreactors be used at a watershed scale? So those are the three questions that frame my talk today. Why treat the drainage water? I'm going to do a little interlude here and talk about a paper that we published here in the last year that looks at different strategies for reducing nitrogen losses. And we've heard much about two of the strategies already today. And the first one you see here are the management strategies, and it's the application of fertilizer, the timing, the type of tillage, those kind of field operations. In our study, we actually looked and considered cover crops as kind of part of the management strategy. And I want Fabian a picture of the coated urea so I can put it up here. I've seen a couple of things that I need to add today. The structural conservation practices are the ones that you see here, and I'll be talking about this, the starting from the bottom, and I don't know what kind of pointer I've got here. You see a woodchip bioreactor, saturated buffer, which are put along the stream corridors to infiltrate water there. Constructed wetlands, or wetlands would be a way to treat afterwards a structural practice. Okay, good, thanks. And a couple other types of bioreactors. This is a denitrification wall. So we're going to focus on this particular strategy. But the third one is the vegetative practices, which include putting more perennial plants on the landscape. And Marshall's talk, he talked about that alfalfa, a year and a half. That was kind of interesting. I go back to my farming experience, and we had oats and we had alfalfa, and it's kind of going back to that. So buffers, maybe more, basically any perennial that will give the same kind of environmental benefit that CRP might give. So those are the three strategies. In general, the reduction in losses go generally in this is kind of a concept drawing, but obviously if we put everything into deep-rooted crops, we won't have much nitrogen loss. And so that's kind of the structure of that. Why did I put an elephant up here? Well, this was the title of our paper, actually. And you can see there are a couple colleagues there from Iowa and one, Reed Christensen, who was in Illinois, but now is in Minnesota. And I'm going to give you highlights from this paper. If you want to look at it, that QR code will get you to the abstract. and you can contact me if you want the paper, but we basically looked at these three strategies and picked information off the nutrient reduction strategies of these three states, Iowa, Illinois, and Minnesota. And so generally we lumped them, and these things could be lumped. I was thinking of Marshall's project there. It could be nitrogen, it could be infield management, or it could be perennials. So it's not really clean, but in general, the orange ones are the infield management and the green ones are land use change. And then the blue ones are the edge of field conservation practices. And we used numbers out of those documents, which we're almost 10 years old now, but we put it all together and took some estimates of what it would take to get to a 45% reduction in nitrogen load. And Brad alluded to that at the beginning of his talk. That's kind of the goal. And so we looked at benchmark, where are we at today? And this is just a high level thing, looking at the fraction of reduction for each of these strategies. And as you see right now, we're over here. I'm going to jump over to the high, and I'm not going to justify what we did. If you want to know, look at the paper. But if we assumed that maximum return to nitrogen was put onto every row crop acre, cover crops were put as far and wide as they could be, that would be the result right there, the orange bar. And we assumed going 50% more than the maximum CRP acreage that ever was, which is a few years ago now. So those were the assumptions made there. And if we said we had to get the rest of the nitrogen reduction from edge of field or structural practices, that's what the blue represents. So basically what this graph is telling you is that as we go on and try to get deeper into nitrogen reductions, the edge of field practices will probably take a larger role. So the second question is, what is a woodchip bioreactor? I'm curious, how many people know what a woodchip bioreactor is? So almost all the hands went up here. So it's pretty common. I threw up some numbers here. It's usually something at the edge of a field. That's typical. I put 60 acres plus or minus, could be 20, could be 80. Here's some pictures from the Iowa Soybean Association to walk you through the process. It's digging a trench, basically plumbing it, using control structures to hold a water table in the woodchip bed. It's important to do. There's usually one on the inlet and one on the outlet, and dumping in the wood chips. This one is particular. They had it sized for 2 loads. So that's what we're seeing here, spreading of the chips, and then the spoils tend to go on top of the soil cap. So that's what a woodchip bioreactor is. This is another diagram of a research bioreactor that we had. We had some of them out in Wilmer. I know some of you were out there a few years ago. And I'm using it to show kind of the path of the water from the inlet here, the yellow arrows, to the outlet. And that period of time we call hydraulic residence time. And we like to see that between 8 and 16 hours, plus or minus. It can be shorter during the peak flow and can be longer at the tail end. But during that period of time, microbes use up the oxygen that's dissolved in the water and then go into anaerobic mode and start to breathe or respire on the nitrate. And so we know from our measurements that when that flow reaches about 1/3 of the way down the bed, the oxygen is below 1 milligram per liter. So it doesn't take very long for the conditions to be right. Now, I assume that some of you stayed to get your full CEUs, and I think that's great. This slide, you'll earn your CEU on this slide. So when you go home tonight around the table, you can tell your kids or your spouse, look at the exciting thing that I learned today about microbiology. Basically, what the principle of operation here is it's anaerobic respiration. And the players are, of course, at this point, the nitrate ion is in solution. It's in aqueous form. A carbon source is needed. This is all about transfer of electrons. And I think this is still mysterious. I'm not a microbiologist. I'm an engineer. I just plumb these things and look for help when it comes to the microbiology. But the carbon source that we like to use is wood chips. It provides the carbon. It also provides a structure for water to flow through. The other players are the little microbes, and they just come in with the drainage water, just build it and they come literally. And they will colonize on the wood chips and within the pores of the wood itself. And they're the ones that do the work. Actually, there are enzymes in their cell walls and between the cytoplasm and the cell wall that mediate the nitrate so that it goes from, it takes a couple electrons on and goes to nitrite. Which is in a fairly low level as this process is going on. And then it becomes nitric oxide, which it's still in the aqueous form. And the next step, though, is going to nitrous oxide, which is a greenhouse gas. And now it's in gaseous form. And the last step then is to convert to nitrogen gas and go back to atmosphere. So that's how this system works. And you've heard about denitrification today in the field. We don't want it to happen there because it's going to go flash off instead of to go in the corn plant. But this is at the end of the line. We can use the same process to keep nitrate out of the water to reduce the amount. So why do we want to treat the water? What is a bioreactor? How does it work? Now we're going to talk about some specific and a specific project that's located 40 miles south of this civic center here. You can see Faribault County is mid-Minnesota, east to west, and just above Iowa. And the site is just north of Blue Earth, which is where the Jolly Green Giant is, if some of you know, just south of I-90. And the site is about 3 miles north of town on County Ditch 62. So this is a closed tile. And the watershed there is 616 acres, almost a square mile. So this is much larger an area to treat than a typical field, one single field. So that's what makes this unique, very unique situation. I had to groove with Brian when he said, when we build a new plant, you know, the first ethanol plant, all kinds of things happened. Well, this is the first of its kind, and all kinds of things have happened, which I'll share with you. We found out about this. I did from Mark Dietrich from the Department of Ag. He was working with the local folks and the engineer. ISG did the engineering, and we learned about it. Asan Ghani there on the right was a postdoc working for me at the time. So we did interact with the engineers a little bit on the design side, and we jumped in to help monitor the performance. So the construction went on in the winter and spring of 2016. Flow began in April there, and we spent that summer then putting in equipment, and so we could measure flow out of the watershed, the concentrations of nitrogen, phosphorus, and other things, and out of the ends of each of these 3 beds. This is what makes this one unique. There are 3 beds, and the flow runs in parallel, but the inlets they're cascading. So the typical flow is straight to the Blue Earth River, which is about 900 feet beyond that dotted blue line. So we are able to pull up the stops and send water to the bioreactors. If the flow is too much, it will just bypass. But once the flow exceeds that of the first bed, it moves to the second one and so forth on down to the third one. And if there's any overflow, it goes back into the county tile and goes down some riprap down to the river. So our objectives basically were to see, can we treat a decent percentage of a watershed flow, not just a field, and also to confirm the nitrate removal performance. We think it should be the same because it's wood chips and so forth, but we set up to look at these questions. And so we'll give some results here. Beginning in the September of 2016, I'll talk about 2016 through July of 2017 when things dried up. So it was basically one water year for us. And the interesting thing here is it was very wet. You can see for the period, the total period there, it was the 6th wettest in 45 years. But in particular, from September through April, it was actually the wettest in 45 years at this location. So another unique thing was that there was liquid water events, rain events each month, at least one. I remember Christmas that year, about an inch of rain. I think it was on the 26th. And one other thing that's very important to this, the outcome that we have here is that rain. Dennis talked about rains in the fall and the spring. This was after the crop was harvested. So you can imagine 3.5 inches of water. It moved some water and sediment. Here is the flow from the watershed. Along on the bottom here, just to give some ideas, to try to treat 162 million gallons of water over this period of time is pretty amazing. 10 inches of flow, or about 26% of the precipitation came off, which I think is pretty typical for Minnesota. I think Dr. Sands was my PhD advisor. He'd say 27% or something like that. It's pretty typical in terms of depth. And just to give you some idea, at the peak, 3,000 gallons per minute, I think that's about 3 quarter section center pivot irrigation pumps running at the same time. And it all comes through this 24-inch tile. The tile can run at about 2/3 full. It's pretty amazing to look down there and to think this is just 1 square mile. So I'll talk a little bit about flow through the bioreactors themselves. Now the colored lines show, the green one shows the amount of flow treated by the first cell, then add on up to the light blue line will be to the second one, and then the darker blue line shows the treatment of all of them. And you can see in September, things started off working about the way they're supposed to work. However, we had that very large event, and we weren't sure why the flow slowed down. I had some other theories about pressure and stuff like that, but we didn't know for sure what was going on because it seemed like everything healed itself basically and it ran fine. But again, in the spring when we had probably rain on frozen ground, we had depressed flow again. So when we've just published these results, we've looked at the time when they were working as they should be working to come up with values here. And we found that there was about 55% of the flow that was treated during this period of time. One thing you can notice though is all beds were not flowing equally. We had trouble getting equal amount of distribution of the water to the beds, and part of that was because of the particle sizes in the third bed. There were wood chips that were locally ground basically, and the particle size was very fine, and so there was a restriction to flow. Saturated conductivity was low, and so we were never able to get full flow out of each of the beds. So I took a look at, well, what if all the beds flowed as much as the best bed flowed? And that's what we have here with the red line. And in that case, we would have treated about 79% of the flow. So we'll look at nitrogen results now. These are the nitrogen concentrations. The black at the top, the little black diamonds are the concentration coming out of the watershed. You can see on the scale on the left about 15 to 20 ppm. I think that's pretty common. And over this entire period, we talked about nitrogen today and the cost of nitrogen. That's how much nitrogen was lost, over 10 tons, I guess. 11 tons, 35 pounds per acre. That's probably big, but again, this was a very wet period. As Brad mentioned, sometimes we can get the concentrations down, but the volume of water carries the load. So the idea of the bioreactor is to take that concentration down, obviously. And so how that came out is when we look at those included events, the 12 events, we removed about 12.5% of the nitrate. So that includes water that's bypassed when the flow is too high to be treated, that just goes downstream. So about 1,500 pounds were removed during that time. Again, if we had flow passing through each of the beds as we would expect, we would have had about an 18% removal over this period of time. So if we look at just the water that's passing through the beds themselves, this was the reduction. It averages about a quarter for the water that actually passes through the bed. And that's pretty typical with research in Illinois and Iowa. And we've got the gallons or GPM basically, or gallons per, miles per gallon of cars. We rate their efficiency, how many miles per gallon. And that's what we have for bioreactors. It's the removal rate, how many grams per cubic meter of wood chips per day are removed. And you can see the range here is from 2.5 to 6.5. We typically think 2 to 20 is a broad range, but this is very characteristic. So our conclusion here is that it was working the way we would expect for this part of the world. Now, I didn't know if Fabian, he's not looking, but if he was going to kick me out of here if I brought a phosphorus slide in, but I hope that's okay. Hope he looked up. During this period, you can see the losses, the dots are the concentration. During those big events, lots of sediment moves, lots of phosphorus moves, about 1/3 of a pound per acre. And that's pretty typical in agricultural phosphorus losses. But during the included events, it was pretty consistent where about over half the phosphorus was removed, but that was because we were accumulating sediment for the most part. Now, I mentioned these big events had trouble with the flow. Basically, in 2018, we had such a large flow that we could no longer manage the beds. Basically, flow was stopped, and this was one of the reasons. Well, this was the big reason right here. Another 3.5-inch rain, the second one in less than a year at this location. The lower picture here is from a bridge that goes over the Blue Earth River just north of our site by the country club there. So the county got some emergency funds basically to rebuild some things, including the bioreactors. So we dug in and found out what was wrong and came up with a plan. Actually, the engineering rewrote up the plan. I want to point out in the upper left, there was another 3.5+ inch rain in September of that year. So in less than 2 years, there were 3 of those big events. And you can see there were about 5 of those inlets. You can see the Hickenbottom sticking up there, and they might keep corn stalks out, but they don't keep silt particles out. So that's what the wood chips looked like when we pulled them up. We recharged the bed in August and September of 2020. This is a little bit of the construction. What did we do to avoid future problems? There were 2 main things. One, redo the design of the inlet manifold. We found that the sediment really caked up on the inlet manifold, which was a dual wall corrugated pipe. And so between the corrugations, it was packed tight. So we moved to the 12-inch well screen product with screened gravel, clean gravel, to allow some space for the water to move any sediment out. And the next thing that we did was to develop a sediment cutoff system. We monitor turbidity in the main line, and then we've got a little program. When it goes up, the gate comes down and actually shuts flow off. And while in the intervening years here, we monitored this to see that the turbidity rises very quickly and subsides relatively quickly too. So this slide actually shows how that whole system works. It's a little busy, but the dotted red line here is the turbidity, and this is the scale over here in NTUs. So you can see when the flow is right here. Black flow is the system flow from the watershed. So when that goes up, turbidity goes up, and you can see the turbidity comes down much quicker than flow. And so basically we shut off the teal line here shows when the gate is shut. So in this case, it was shut for about 45 hours. And so all the flow bypassed. Then when it slowed down, we opened it up and you can see the blue line then is the flow through the bioreactor system. So that's in place now. So this is a kind of lessons learned thing. Again, first ever in the world largest bioreactor in the States here. But the involvement of the local drainage department, soil water conservation district personnel, the engineers, they are actually in the room right now. They didn't walk away from the project and they came out, helped us. They helped with the redesign. So that was good. And producers also have chimed in and been involved, and that's been a real positive part of this project as well. Having one big bioreactor replaces several small ones. And so there is a sense that management is centralized. The Soil Water Conservation District people actually have learned how to do some of the basic maintenance and learn how to operate this system. Having all the water in one place makes it possible to know exactly what the load in and load out is on a 15-minute basis. We've got nitrate sensors in there right now. So nutrient reduction verification is, I think, more possible with a system like this. And coming off of a watershed, that the descending limb of the hydrograph is longer, so that the flow tails out more than it would from a field only system. That's another positive. And as I mentioned before, we feel that this has basically performed as expected, and this cascading design is legitimate. On the challenges side, there are costs associated when you go with design, construction, and maintenance, no doubt about it. There's certain things about the design, the head, the plumbing, that need to be paid attention to. Media, the number of cubic yards of wood chips is interesting. When the recharge came, there were times where we had to wait for a few days for more wood chips to come. So that can be an issue. The media quality is also important in the bioreactor. The larger, more uniform sized chips are advantageous. Sediment, I've talked about the challenge of that, and these increased frequency. Any of the edge of field practices, we have to think about what do we do in terms of when big events come to protect them, and so that they can continue to function through these things. Basically, we concluded at the end of our paper that we think this kind of system could treat 60 to maybe 75% of the flow and remove probably 14 to 20% of the nitrate end load. There have been a lot of organizations and persons, I've listed some of them here, that have contributed either with money or with in-kind labor, and we're very appreciative of that. And the technicians have done a great job here. It's really a pleasure for me to work with them. Todd Schumacher is my technician at USDA. Chad Villand is from the Soil Water Conservation District there in Blue Earth, and Scott Madison has helped us on the hydrology side and doing a lot of flow calculations for us. We appreciate them, and they work well together. Finally, in the lower right-hand corner is the co-authors on the paper, which has just been accepted. I wish I had a DOI. If you're interested in the paper, you can email me and I'll get you a copy as soon as one's available. But Ehsan, I mentioned him, Brent Dalzell and Mark Williams also helped me on the paper. So that's it. Thank you. Questions? Okay, first one is on how much goes off as N2O versus N2, which would reduce environmental benefits. Right, pollution trading is an issue with denitrifying bioreactors. We have done measurements in the lab, and we're seeing less than 0.9% of the nitrate coming in going out as N2O. So this has been measured in the field at Iowa, where they have 9 bioreactors. They did a study there with the residence time of 2 hours versus 8 hours versus 24 hours. And they found out when the residence time is too short, 2 hours, then there was quite an increase in nitrous release. So that's why design wise, it's important that we design them to have more of an 8-hour residence time, because obviously it takes time for those microbial transformations to go on. And if that time is too short, then there's more likely to release of N2O. But most of the studies show not that much N2O being released. How does water temperature impact the residence time? Well, this is very interesting. I'll answer directly because the viscosity of water, believe it or not, is quite different at 5 degrees C than it is at 20 degrees C. And that's kind of the range. You wouldn't think that water is more viscous at 5 degrees, but it is. And so it would retard the residence time. I don't think anybody's really looked at that or tried to measure that. But what temperature does do is slow down the microbial reaction. And so that is a function we talk about for every 10 degrees centigrade change, there's a rate change of 2 to 3. So in other words, water passing through at summertime temperature of 15 degrees C, when it's in March and April, it's 5 degrees C, that's 10-degree difference. So the rate would be only 1/2 to 1/3 of what it would be in the summertime. So that's the effect that temperature can have on these things. Marshall? Yes, great question. Marshall asked about the sources of the wood. Are different species, or has biochar been used? There's kind of 2 questions. And the answer I would give for the species don't seem to matter too much, other than avoiding things like black walnut or woods that are resistant to decay. Cedar, those are not something we want in there because they won't release the carbon that's needed for the reaction. There is the first year, there's more carbon that's available in the carbohydrate form. And so these 10 to 20 removal rates tend to occur in the first year when there's more carbon. And then after that kind of settles down, then we're back under 10. And so it's more a function of age. The next question about the biochar, yes, people have used biochar and they've come up with a mixed bag for results. Sometimes the biochar has a negative performance on the microbes, but other people have seen where biochar can actually, it can slow down the nitrate, retard it a little bit, so allow more time and actually colonization surface area improvement. So some people have seen an improvement and some people have seen it go a little bit the other way. So thank you. It's a good question. Are there any leads on strategies that would make recharging a bioreactor faster, easier, or cheaper? The work required to recharge seems to be limiting, and I agree with that. Absolutely. And this is, I'm an engineer, so I think about this. One of the things that the problems, for example, in Denmark, we've got someone from Denmark here. They're kind of one of the leaders in putting these things out there. They leave the tops open and they actually plant perennial plants into them. But when they put in a bioreactor, at 5 years, they're required to put in 50% again as many wood chips to recharge them, and they leave the top open so they don't have to scrape off the soil. So I think there definitely are some things that we need to think about from a design point of view that would make it easier. I'm sorry if this was addressed. Is there potential for methylation of mercury? No, I didn't address that, but that is a very good question. And in wetlands or bioreactors, again, when we talk about the residence time, if the residence time is too long, it's possible, especially under some summer and warmer conditions, to remove all the nitrate. And we don't really want that to happen, because once the microbes have used all the nitrate, they still want to respire and gain energy. And so what do they go for next? They go for sulfate, and they reduce that, and that becomes hydrogen sulfide that smells like rotten eggs. And that's when we know the residence time is too long. One of the things I didn't mention, the NRCS has a conservation practice standard for bioreactors, and they require that in the outlet stop logs that hold the water back, there needs to be a hole that will allow the water to drain out within, I think it's 48 hours, to avoid this problem of too long of a residence time. Sulfate, once it gets to sulfate, then I understand the microbes that do sulfate also can put methyl onto the mercury and make it bioavailable. So we want to avoid that. Good. Thank you.